Now let's talk about force equilibrium of stress element. For this thin plate stress element, notice that it is the side view of it. It has the thickness of dx in the longitudinal direction, while the cross-section of this thin stress element would be look like this. It is a possible cross-section. It has a height of y2 minus y. If we further cut the stress element in this way, then for this piece of stress element, it has a width of w, but w is dependent on y because when you shift this differential stress element upward or downward, there will be change. That is, the change of y will change w, so w is a function of y. Then this differential area will become wy times dy. So this is wy, while this is dy. For this thin plate differential stress element, you can see there are two forces acting on it. One is the direct stress caused by the bending on the left hand side. Another one is the direct stress caused by bending on the right hand side. In the last tutorial, we mentioned that we can draw a distribution of direct stress with respect to x, maybe like this, or maybe like this. So in such case, the direct stress on the left hand side may be different from that on the right hand side. Therefore, the variation of direct stress on left hand side and right hand side would cause force in equilibrium. That is, we must add another force to keep it equilibrium. So in this way, since at the upper end of this stress element there is no force, then there must be a horizontal shear force that holds this piece of stuff in equilibrium. So in horizontal direction, there is a shear force VH. Now we consider this piece of differential area dA, where dA equals to wy dy. Then for this differential stress element, its dimension will be dx times dA, which is dx times dy times wy. In another word, the differential force acting on it will become dF equals to sigma dA. The reason is that on the left hand side and the right hand side, it is given a stress distribution on the surface, and the force is given by the integral, the summation of the stress and the differential area. So we can say for this piece of differential area, the differential force acting on it will become the local stress, sigma, times the differential area, which is given by wy dy. Then the net force on the left hand side surface and the right hand surface can be given by integrating this differential form on the left hand side and right hand side. On the left hand side, sigma x equals to minus my divided by I, and we know that dA equals to wy dy. Further, we know that since we are integrating with respect to dy, we are interested to the range of y, but it is clear that the range of y is from y to y2. Therefore, we just write the integral of y to y2 to get the net force on the left hand side caused by the bending, which is F1. Similarly, for F2, the stress given by bending is minus m plus dm y divided by I. dA equals to wy dy. We integrate this from y to y2 to get the net force on the right hand side caused by the bending on this differential stress element. Now we have F1 and F2. Then we consider the shear force acting on the stress element, which is this force. For this force, it is exerting on a surface of thickness dx, or the length dx, and the width wy. So imagine it is a stress element. You have a thin plate stress element. F1 looks like this, F2 looks like this. The thickness is dx, the width is wy, the height is given by y2 minus y. Then what is the area of this surface? Recall that this surface equals to the lower base, so those two surfaces has the same area. So what is the area? It is given by dx times wy. Therefore, the shear force acting on this surface is given by the shear stress times the differential area, Vh equals to tau h times dA where dA equals to Wy times dx. Now we have all those things ready, and by the force equilibrium we know that F1 minus F2 minus tau h equals to 0. Then we substitute all those forces as well as this one into this equation. Next, we try to simplify it by observing that the my divided by I term can be cancelled out. Then the things left here is y dm divided by I times wy dy integrated from y to y2 minus tau h wy dx equals to 0. This equation seems a little bit strange because, okay, why there is dm and a dy existing in the same integral, and why there is a dx existing here. So don't worry, there is a way that we can do it. We divide both sides by dx. The left hand term will become the integral from y to y2 dm dx times 1 over I times y wy dy. And for the right hand term, you just cancel the dx out. That's it. So those two stuff, since they are irrelevant to y, then we just take them out to be the constant. Then the equation can be written in this form. If you have read our tutorial notes carefully in the last tutorial, we mentioned a very important relationship, which is the shear force equals to the differential of moment with respect to x. That is, v equals to dm dx. Therefore, this term is simply becoming the shear force acting on this cross-section. Besides, since we know that dA equals to wy dy, we can write this wy dy to be dA with respect to an area. One important observation is that the area you want to integrate with is actually come from this lower and upper limits. So this lower and upper limits give you the hint that you should integrate the area which is above the level of y of this cross-section. So in the later examples, you will see the application of this formula and how do we compute it. Another observation is that this integral is rather familiar, right? We introduced in tutorial 0 that it is the first moment of inertia with respect to the horizontal axis, which is qx of y. So in the later stage, you will do some examples that you will find the first moment of inertia above a certain level of y for some problems. So you may see those things later. So now this equation is becoming 1 divided by I times v times q minus tau w equals to 0. Then we can rewrite this equation to be tau equals to vq divided by iw. It is still talking about the horizontal shear force. So now we get a conclusion that the horizontal shear stress inside the beam is dependent on two variables, x and y. It equals to the shear force acting on this cross-section times the first moment of inertia of an area above the level of y divided by the second moment of inertia of the entire section times the width of that particular height, particular value of y. So now you can see the horizontal shear stress is dependent on two variables. But no worries, we can simplify all those things quickly. The first observation is that the vertical shear stress is equal to the horizontal shear stress. Then tau h is just becoming tau. Also, the shear force inside the cross-section is just the shear force, which is v. Then this will become v. The first moment of inertia, we just use another notation, we simplify it. It is just q. For the second moment of inertia, actually there is nothing worth us to simplify. You just bear in mind that this moment of inertia is evaluated with respect to the horizontal axis. The width of the cross-section at a particular position y is just w. Finally, you will get this very important shear formula, tau equals to vq divided by iw. So if you didn't go through the proof I just went through, then you would have trouble to understand all the terms inside this formula. What is tau? what is V, and especially what is Q. So Q is a very strange quantity that you need to think of it. And the moment of inertia, I believe you have already learned how to compute it in the previous tutorials. W is the width. So after going through all those proof steps in the previous slides, I believe you are now familiar with this equation. But still, recall some major restrictions regarding to the use of this equation. It is only useful for axially symmetric cross-section. So recall that for this direct stress formula, in the last tutorial, we tried to write a general version which is applied to all the cases, all the cross-sections. So the general version is given by sigma c equals to minus mx Iyy minus Ixyx divided by Ixx Iyy minus Ixy squared minus my Ixxx minus Ixyy divided by Ixx Iyy minus Ixy squared. So we described such a formula in the last tutorial for you to challenge, or anyway, it is something in year 3, but there is such a formula, and unless you make this cross-section to be axially symmetric, then Ixy is non-zero, then this direct stress formula will become much more complicated, and this derivation will be not that simple. Besides, another important point we need to point out is that this equation just gives an average shear stress across the width. The shear stress is actually non-uniform across the width in the real case.